Yeah, so welcome back everyone to SL2 group, which is kind of morphing into SL3 group, and then maybe micro local sheaves group. So we'll see what happens throughout the semester, but at least for the next few weeks, we're going to be having talks about SL3. But before we kind of start doing that, we wanted to have Nate talk about something that he did last semester, which came out of discussions from the SL2 group. So yeah, it's my very great pleasure to have Nate Harman here speaking to us about a categorical approach to representations in defining characteristic.
Yeah, thanks for having me. And yeah, so this is, I guess, still part of the SL2 group, but kind of nothing that I'm doing today will be SL2 specific. And well, we'll see just what level of generality I want to talk about at various points. But yeah, okay, so this really came out of something last semester, and really it came out of sort of just a thing that Jordy said right at the end of his talk, which was the very first SL2 seminar. So I have a screenshot of that. And so we have G in this notation is the FQ or Q to the R points of an algebraic group. And Jordy's dream that he has highlighted there is that representations of the finite group should be representations of the algebraic group, but where we force the Frobenius twist to act of order R, of this R and this Q to the R. So this was kind of one of the last things that Jordy said in his opening talk for this group, and I sort of latched onto it and decided that this was a thing I thought was interesting, want to think about. So yeah, so really the goal that I had and that I want to kind of explain today is I want to make Jordy's dream come true. I want to explain, you know, a sense in which this is true, and maybe sort of why this is not just like a good sort of guiding idea to have in mind when you're thinking about representations in defining characteristic, but like a literal, precise theorem that we can state. All right, so this is the sort of guiding idea that I want to explain what it means to sort of force the Frobenius or a power of the Frobenius to act trivially, to act by the identity. All right, so I'm gonna have my own setup, sort of slightly different from Jordy's, but close. So I'm gonna have an algebraically closed field of characteristic P, and this will be like the field of definition for all of my representations. Great, and then I have Q, which is gonna be a power of P, and I'm not really gonna care what that power is. I'm sort of dropping the R from Jordy's setup, so I just have a single power of my characteristic. And then I'm going to take G to be a simply connected semi-simple algebraic group defined over FQ. And I'm going to relax those constraints at some point, but to start, it'll simplify my life to assume it's simply connected, semi-simple or even simple algebraic group. And all right, then the main sort of actors in this are G itself and GFQ, which is going to be the FQ points of G. And this makes sense because G is defined over FQ. So I sort of have a way of defining G over FQ, and then I can ask what the FQ points are. I get this finite group. Great.
Nate.
Yes.
So do you also take the non-split one? I mean the twisted one for the GFQ?
So for now, let's just think in the simplest setting. I will relax everything at some point in this talk.
Thanks.
So for now, I mean, even just thinking like G to be SLN is maybe what to start, and then at some point all the training wheels are going to come off. But yeah, so I can, yeah, eventually every case will be handled. But let's start with this, yeah, G is SLN is what to have in mind right now. Great. Okay, so I have G. I have the FQ points of G. I have this Frobenius homomorphism from G to itself. And again, this is an actual homomorphism on my algebraic group because it's defined over FQ. So right. So if it was defined over some other different finite field, you might think of it as being a map from G to some Frobenius twist of it. But I really want to think of it as a map from a group to itself. All right, and then I'm in sort of abusive notation. I'm also just going to use this FR to denote the sort of Frobenius pullback of a representation. So I pre-compose my representation with this Frobenius twist, and this composition gives me another representation of G. So this operation, is a functor, and the reason why I want this notion of Frobenius twist, I want to be sort of clear about it, is this is the one that is k-linear and, well, monoidal. But the sort of other natural Frobenius twist functor is only sort of Frobenius linear. So they're closely related, but this is the k-linear one. Yeah, okay, so this is the setup, at least to start. And so I want to, go towards proving a version of Jordy's dream. All right, so are there any questions about the setup before we get going? All right. So I want to first prove an initial version of this theorem, a sort of decategorified version, but it'll hopefully kind of motivate what's going to happen in a bit. So I want to talk about the Grothendieck ring of these groups, by which I mean sort of the Grothendieck group of the category of representations with the product structure coming from the tensor product of representations. So since we have a natural monoidal structure on these categories, it gives the Grothendieck group an actual ring structure, and that's the Grothendieck ring. And so I want to formulate a version of this dream conjecture just at the level of Grothendieck rings, and sort of maybe prove something there, and that'll be a sort of sanity check that something like this is even true, and then we'll make something more categorical. But okay, so what's a reasonable thing to expect on the level of Grothendieck rings? Well, here's the statement. So if I restrict from G, the algebraic group, to the FQ points, this induces a homomorphism of rings on the level of Grothendieck rings, and the kernel of this homomorphism is an ideal, and that ideal is generated by differences V minus Frobenius twist of V for all representations of G. Whether all representations or all irreducible representations, it's the same. All right, so this is saying that we're quotienting by kind of exactly setting a representation and its Frobenius twist to be the same thing. So this is, kind of, I think, a natural way to interpret this dream conjecture, at least at the level of Grothendieck rings. One thing I want to highlight here is this is really a ring property. So this ideal is generated by these differences, V minus the Frobenius twist of V, but it's not spanned by them. So it's not the case that we can just quotient by kind of the subspace of the Grothendieck group generated by these differences. We really need to take an ideal. And this fact that you actually need to do this, you can see it kind of easily for like GL1, which is maybe not actually in the setup I have here, but you can check it by hand there, that you really need the product structure. All right, so I'm gonna go through a proof of this. It's kind of simple and straightforward. But before I do, does anyone have any questions or comments just on the statement of this this decategorical version? All right. So this is going to be a short, nice proof. And so one half of it is kind of obvious. This ideal is definitely contained in the kernel of the homomorphism.
Can I just confirm? So when you write K0, you mean it's for the category of all modules. I mean, the Grothendieck's notation up there, yeah, is G0. So just, yeah. I mean, you said it, but it's just, yeah, as a general remark that people in representations of finite groups would maybe use G0 for that. Okay.
Ah, great. Yeah.
I mean, maybe in describing characteristic, maybe they use K0. I don't know. Just small remark.
Yeah. So I think of it as like K0 is an operation we apply to a category.
Yeah. No, I understand. Yeah, I understand.
Yeah. Great. Okay, so half of this is kind of clear. We know that since the FQ points are the fixed points of the Frobenius, that any representation of the finite group is going to be just kind of fixed by this Frobenius twist operation. So we definitely know that anything of the form V minus the Frobenius twist of V is in this kernel. And then also the fact that it's a homomorphism of rings just implies that this ideal is in the kernel. So really, we just need to check that it's actually everything. If there's not more stuff in the Grothendieck ring that gets killed. And so this is going to follow from like the two standard facts about representations and defining characteristic that I know. So the first one is the Seinberg restriction theorem. So if I have a Q restricted highest weight for G, then I can take there's a unique irreducible highest weight representation of G with that highest weight, and I can restrict it to the FQ points, and that remains irreducible. And then moreover, every representation of the finite group appears this way. Right, so this lets us kind of match up representations of the finite group with some nice subset of the representations of the algebraic group. Okay, so now that we have these L lambdas for the Q restricted weights are sort of a nice natural system of lifts of the Grothendieck ring downstairs, the one for the finite group. So in order to prove this theorem that I'm proving, you just need to show that for any other highest weight, mu, that we can write mu as, some linear combination of these Q restricted highest weights, the modules with Q restricted highest weights, plus something in our ideal. This ideal generated by these differences. All right, so this is what we need to check just concretely. And now let's do that. So the other fact that one who doesn't know things about defining characteristic representations might know about defining characteristic representations is the tensor product theorem for algebraic groups, for simply connected algebraic groups, which tells us that if we have a highest weight that's not Q restricted, that it decomposes as a tensor product of Frobenius twists of Q restricted, of irreducible modules with Q restricted highest weight. So this is one of the sort of foundational theorems about representations of algebraic groups in positive characteristic. And if you're worried about whether it's Q or the underlying group P, it's true either way. Each one of these tensorands itself might be a tensor product of things that are P restricted and they're P Frobenius twists, but you can group them like in chunks based on if Q is P cubed, you take sort of 3 of them at a time. Anyway, it's just the Q version of the Steinberg tensor product theorem. But all right, now this is good for us because each one of these terms we can replace by something smaller, right? So I take each one of these terms, a Frobenius twist of L of lambda, and I get to replace it by the un-Frobenius twisted version, because that difference is in our ideal, right? So now up to kind of junk in this ideal that we have, I can just write my L mu as a product of some L lambdas, which are all Q restricted, plus something in my ideal. And this is still not quite what we want. I want to write it as just a sum of things of this form. But now the point is we can just repeat this process, right? So each one of these terms I'm multiplying together are smaller than their corresponding Frobenius twists that I was previously multiplying together. So in particular, we can just do induction on the weight lattice to see that, if we decompose this product, all of the terms that appear in the product are smaller than the thing that we started with. So by induction, we can write all of them on the form we want. Yeah, so that's like the entire proof of this version 1 of the dream. And so it really just follows from the restriction theorem and the tensor product theorem. Yeah, so that's the decategorified version of Geordie's dream. And now I'm going to want to, categorify it. But so does anyone have any questions about this theorem? Great. So I think that's, fairly, straightforward and cute proof. But now let's put more categorical things in the mix. So to do that, though, I want to reformulate what is happening here. So the point is, this ideal is not, it's not a general ideal. It's kind of a very special ideal. It's generated by these kind of specific elements, and we can reformulate this statement as something categorical in the category of rings. So what this is saying is that this restriction to the Grothendieck ring of the finite group is a co-equalizer of the identity map and the Frobenius twist map on the Grothendieck ring of the group. Specifically what that means is that the two compositions from kind of the left copy of the Grothendieck ring of G to the Grothendieck ring of GFQ, both of those compositions are the same, and moreover, this logarithmic ring of the small group is universal with this property, right? So if I have any other map out of K0G to some other ring such that these two compositions compose to the same thing, it has to factor through this. Right, so that's what it means to be a co-equalizer. This notion of a co-equalizer is just sort of a general categorical notion, and kind of by usual universal property stuff. If one exists, if you have two maps between two objects in a category, if their co-equalizer exists, it's sort of unique up to isomorphism. Okay, and this whole reframing in the level of rings, there's really no content in this reframing. For rings, co-equalizers are a very straightforward thing. It's if you have two homomorphisms from one ring to another, you just take the ideal generated by stuff of the form, G of R minus H of R, and quotient by that, and that's the co-equalizer for rings. So this notion of a co-equalizer, it's some sort of categorical thing that you can always ask, does it exist, and whatnot. But for rings, it's a pretty straightforward construction. So there's really no new content in this reformulation, but it's a sort of convenient language to use. So in particular, it's convenient for the following: the actual categorical version of this dream theorem. So now let's look at actual categories of representations. So I have rep G and rep GFQ. These are the categories of finite dimensional representations of these groups. We have the following. So these form a co-equalizer diagram in the category of pointed Tanakian categories. So I will say what that means in a second, but I want to maybe sort of pause and let this sink in, that this co-equalizer notion really is saying that the Frobenius twist and the identity have to act by the same thing. This is really sort of forcing the Frobenius to act by the identity, which is exactly what I set out to do in the beginning. Great. So I hope it's clear that this exactly categorifies the previous theorem. What is maybe more surprising or something is that this is true for any algebraic group. I don't need simply connected, reductive, semi-simple, anything. This is kind of unreasonably general. So everything that should both excite and worry you about what I'm about to say. Great. Okay, so I'm gonna give a proof of this. It's actually not that hard, but maybe this is a point that people want to ask something or.
In this statement, are you only considering monoidal functors?
Yeah, so there's something that I really need to clarify before I prove this. What do I mean by the category of pointed Tanakian categories? What is a pointed Tanakian category, and what are the maps between them? So yes, everything will be monoidal, and even stronger than that. That will be on the next slide probably, or the slide after that.
Does algebraic group mean linear algebraic group?
Yeah, this is true. Linear algebraic group. Yeah, something. Yeah.
And is the Grothendieck group statement? Oh, sorry. Is the Grothendieck group statement definitely false for any algebraic group?
Well, maybe as Eric well, so it's definitely false for non-linear algebraic groups. But I don't know for a more general algebraic. So it is true for the decategorified version. It is true for, say, GLN. And I tried, I tried proving it for general reductive groups, connected reductive groups, using this description of Lubeck and Brunot, I think, are the people. And I couldn't quite prove it in the full generality, although I think that might be my failing and not the theorem's failing. So I'm not sure. And this is something I'll sort of maybe mention at the end. I'm not sure to what extent the decategorified version actually holds. Yeah, which is why I was careful to set myself up at the beginning with a very restricted class of groups where the proof was easy, but then yeah, I will try to work out eventually what the actual scope of that theorem is. But I should also say I'm telling this story sort of in reverse. I came up with this categorical formulation and then thought maybe I should do a sanity check and see what it does for the Grothendieck ring, and was sort of pleasantly surprised for GLN. But yeah, so this is true for any, I should say, affine algebraic group. All right, so let me, before I go into proving this, I have to sort of unpack what I actually mean by this category of pointed Tanakian categories. So let's do that. Okay, so I'm going to have a k-linear abelian category C, and it has to satisfy a bunch of stuff. So already it's k-linear and abelian. All of the spaces of morphisms have to be finite dimensional. So yeah, it's finite dimensional k-linear. Every object is finite length. That's a finite length Jordan-Holder series. Great. We have a monoidal structure, and it's a k-linear monoidal structure, so it's sort of suitably bilinear. All right, it's symmetric, so it has a symmetric braiding. So we have a nice way of making V tensor W isomorphic to W tensor V, such that if we do it twice, we just get the identity. It's rigid, which means there's a notion of duals. The sort of example being a finite dimensional vector space and its dual. The properties that those satisfy, but also a representation of a group, a finite dimensional representation of a group. The dual vector space naturally has a G action, and if it's finite dimensional, that together forms a rigid object. I won't go further into what that means. And then the last axiom we need is that C admits a functor to vector spaces, which kind of preserves everything. So it has to be a, k-linear exact braided tensor functor to vector spaces. And we call this the fiber functor. So this is sort of the setup of Tanakian formalism. And if all of this holds, we say that C is a neutral Tanakian category. And I even put neutral in parentheses. Neutral usually refers to the field of definition. So like a non-neutral Tanakian category might only have a fiber functor in some algebra over your field. But for algebraically closed, this is not really a just Tanakian category. So this is a Tanakian category over K. But I had this one extra word, pointed, which I just made up because I couldn't find appropriate name for this somewhere, but maybe one exists. It doesn't exist in Deligne Milne, so blame them. So if I additionally specify what this fiber functor is, and I'm going to keep track of the category with all of this additional structure and fix the functor to vector spaces, this is what's I'm going to call a pointed Tanakian category. All right, so that's all that I mean by that term. And so let me, unpack this a bit and give an example. So if we have a group, just any abstract group, then the category representations, finite dimensional representations, forms a Tanakian category. So for sort of clear reasons, right? This is clearly a k-linear abelian category. Since it's finite dimensional, everything has finite length. We have a natural monoidal structure because it's groups. There's a symmetric braiding where you can flip the order of two tensor factors. It's rigid. Again, that's sort of finite dimensional property that the dual representation of a finite dimensional representation satisfies the right conditions. And it has a natural fiber functor to vector spaces, which is just the forget the group action functor. Right. So for any group, the category of finite dimensional representations is a Tanakian category, and that's the sort of prototypical example of what a pointed Tanakian category is. Okay. So now I want to get to I think it was Tony's question. What do I mean by sort of maps between pointed Tanakian categories? I want to kind of make pointed Tanakian categories into a category, or well, maybe a two category if I really want to be careful about it. But okay, so I want to kind of motivate the definition of a map. So if I have two groups and a homomorphism from one group to the other, so I have this phi from G to H, then I can take a representation of H and I can just pull it back along this homomorphism to get a representation of G. So that gives me a monoidal functor from representations of H to representations of G. But moreover, that monoidal functor is compatible with the fiber functors in the sense that if I have a representation of H, I can either just totally forget the action of H, or I can first, restrict to this copy of G inside of it, and then forget the action. And either way, I just get, the same underlying vector space with no group action. So in this case, the two functors from representations of H to vector spaces are literally equal, which is maybe a weird thing to assume. So instead, I'm gonna define a map between two pointed Tanakian categories as follows. So if I have my categories C and C prime with their fiber functors, I'll define a map or a morphism of pointed Tanakian categories to be a braided tensor functor from one to the other, along with a way of identifying the fiber functors, a natural isomorphism from F to kind of the other fiber functor you get by going through C prime and then down. So I think this is the sort of obvious notion of what a map between a category equipped with a fiber functor should be, hopefully. And then the point of making this the definition is that this gives us this defines a contravariant functor from groups, all groups, to pointed Tanakian categories, where you just take a group and take its representations. So start with your group, send it to its category of finite dimensional representations with the natural fiber functor. And that's functorial in the sense that a homomorphism of groups gives us a morphism of Tanakian categories, of pointed Tanakian categories. All right, so that's what I mean by the category of pointed Tanakian categories. So this is sort of the setting in which this theorem lives, this statement about co-equalizers. But all right, what do we know about Tanakian categories or pointed Tanakian categories? Well, this is really the subject of Tanakian formalism. So I'm gonna, it's a big subject, and there's been it's been generalized in lots of different ways. And so I'm only gonna really state it in a version that suits my needs. But so what is Tanakian formalism? So here's sort of the main theorem in Tanakian formalism. This is Tanakian reconstruction or Tanaka-Krein duality. And this is saying that every Tanakian category, every pointed Tanakian category, so with a fiber functor, is equivalent to representations of a group with the natural, just forget the group action fiber functor for some algebraic group G. And to be really precise, there are these words in parentheses. I really can't just talk about algebraic groups. I need to talk about group schemes. And I might have some pro algebraic group, not one on the nose. But in fact, if the category is sort of finitely generated in a sense, which I won't get into, we can drop that the pro condition. So every Tanakian category is coming from representations of some algebraic group scheme. And I maybe again I should say affine algebraic group scheme to be precise. So that's kind of the first part, and so I should also say I listed Tanaka and Krein and Ravano and Deligne-Milne. This Tanakian formalism has sort of a long history, and the version I'm sort of basing things off of is Deligne and Milne, who did it in terms of algebraic groups, but maybe the earlier versions were in terms of like compact groups. So Tanaka-Krein duality is kind of duality between representations of a compact group and its category representations. But this is the algebraic group version. Okay, so every Tanakian category comes from representations of some group. And moreover, if I have two groups, G and H, then any tensor functor from representations of H to representations of G that's compatible with the fiber functor comes from a homomorphism in exactly the way I described on the previous slide. So it's just a pullback of a homomorphism, and that should be a homomorphism from G to H, because I didn't proofread this well enough, apparently. Great, so that, I mean, these two statements together, I think of as being sort of two of the sort of main things that I call Tanakian formalism. So it's this idea that the category representations of a group, along with all of its bells and whistles, so all of the monoidal structure, the symmetric braiding, and this functor to vector spaces, the sort of the data of all of that is equivalent to the data of the group itself. That's sort of Tanakian reconstruction. And then the second part is sort of also a sort of functorial statement that maps between groups correspond to maps between pointed Tanakian categories. Great, so this is Tanakian formalism, and sort of just translated into the language I introduced on the last slide. This is saying that our taking representations functor from groups of pointed Tanakian categories is actually an equivalence of categories from algebraic groups to pointed Tanakian categories. Where again, algebraic groups, I should really say like pro-algebraic group schemes, but I'll just think of it as the category of algebraic groups. Great. So this is a sort of categorical formulation of Tanakian formalism that kind of groups and categories of representations are equivalent or contravariant equivalent. Great. Okay, so now I would just like to now explain the proof of this theorem from this perspective, and it's essentially trivial now. Now that I've explained this, the point is the FQ points are an equalizer in the category of algebraic groups, and this really has no deep content. If I have two homomorphisms from one group to another, their equalizer is just the subgroup cut out by where the homomorphisms are equal. So in the case for FQ, I'm just saying when is X equal to Frobenius twist of X, and that's exactly the FQ points. So there's nothing in that statement. And by an equalizer is, again, it's sort of universal in the opposite way, in the dual way, and then we're done, because a contravariant equivalence of categories will send equalizers to co-equalizers, and that's it. that's the proof. So I have a bit more, but maybe this is a good place to pause for some questions.
Nate, if you go back to the previous slide, I'm always a bit, so I'm a bit suspicious of your equivalence there, because I feel that so I'm just kind of operating on memory from using Tanakian formalism, but somehow Tanakian formalism sees things up to conjugacy rather than on the nose.
So not once you fix the fiber functor. So this is actually this notion of pointed Tanakian category is really important. So I talked to you a bit about this last term, and I was struggling with trying to formulate this just in terms of Tanakian categories, and sort of the answer is to involve this fiber functor. Maybe let me say why I chose this word pointed, and it'll hopefully clarify why it clears up this issue you were having. So I want to think of a Tanakian category without a fiber functor, as I can take something like I can say I have a manifold, just like an ordinary smooth manifold. I can look at vector bundles on my manifold with a flat connection.
Nate, it's so funny. Like I'd actually typed this explanation in the chat as to why pointed is a good name.
Oh, great.
And then deleted it. So that's really amusing.
Yeah, so that's the point. So I have a manifold. I can talk about flat vector bundles on my manifold, and I have this is a nice category. I have tensor products and duals and everything. It's great. But then choosing a fiber functor is like choosing a base point. And once I choose a base point on my manifold, I can identify this category of vector bundles with a flat connection as being representations of the fundamental group. So picking a fiber functor is analogous to picking a point on your manifold, and then your problems sort of go away. So in a sense that your Tanakian category, your non-pointed Tanakian category, is like representations of the fundamental groupoid, in which you can't really tell the difference between things up to conjugacy. Whereas the pointed version, you've kind of nailed down things, the conjugacy issues.
So what you said is a perfect picture for a connected space. But I think there was an issue. So Grothendieck was complaining that the lean and mean, like rewrote the Sarah-Redress thesis, but he forgot an assumption. It was something like connectedness, like the unit is irreducible or something like this.
Yeah, there's certainly. I mean, I think what I just said, it was really a sort of picture, a motivation for.
Yeah, but I mean, in the axioms of pointed Tannakian categories, you don't need to assume that the unit is irreducible or something.
You might be right. I might have missed one.
Maybe it doesn't matter, but
so I think this is actually encoded in this neutral business that I have my I want, yeah, you're right. I want endomorphisms of my unit object to be K itself, to be the field and not some algebra over it. So yeah, maybe I actually should have included that in the axioms here. And yeah, that I think might address this connectedness issue. Yeah, I mean, there are a lot of axioms, and I was doing this from memory, so you know. Yeah. Any other questions or concerns? All right, so let me, you know, I got a bit more material. So bonus, extra stuff. I'm going to tell you about Frobenius kernels and how they fit into this picture. So let's go back to my original setup where I have a nice simply connected semi-simple algebraic group for the moment. Well, I guess what I'm about to say, it doesn't matter. But okay, so representations of G, in addition to having like the identity functor and the Frobenius twist functor, there's another like supernatural monoidal functor that a category of representations has. It's maybe not one that we think about terribly often, but this functor is the trivialization functor. So this is you take a representation of your group and you send it to the same vector space, but with no group action. And so that is a functor from representations of a group to itself, but it kind of just lands in like the trivial part. So it's maybe not a very interesting monoidal functor typically. And then I say on the Grothendieck group, I'll denote this map by triv in brackets, and it just sends any representation V to dimension of V copies of the unit object, the trivial representation. All right, so that's that gives a homomorphism of rings from K0 to itself. And so the theorem about Frobenius kernels, so I'm going to let K denote the Frobenius kernel because I don't know, I'm bad at notation, is I can take a co-equalizer of this trivialization map and the Frobenius twist, and that's a co-equalizer for rings. So explicitly in terms of ideals, again, this is saying that the ideal, the kernel of the restriction map is generated by things of the form Frobenius twist of V minus dimension of V times the unit. So that's the first part of the theorem. And the second part is just a categorical lift of it to this setting of pointed Tannakian categories. And the proof for both parts is just identical to the previous one. For part one, we still have a nice restriction theorem, which tells us that Q-restricted weights remain irreducible. And then you do the same trick to show that this ideal, the kernel is what we think it is. And for part two, I have two homomorphisms for groups, and they are now, there's the Frobenius twist from G2 itself, and there's the send everything to the identity element homomorphism. And the equalizer of those is the set of stuff that when you Frobenius twist it, it goes to the identity, which is of course the Frobenius kernel. So that forms an equalizer in the category of algebraic group schemes, and therefore we get a co-equalizer in the category of pointed Tanakian categories. So
And
yeah.
So to define triv, you really need that it's pointed. No,
You really need that it's pointed. Yeah, triv sort of. Yeah, you can kind of think of it as like when you have the fiber functor, you also get a like a section of it. Just taking that vector space with trivial G action, and that composition is how you get this triv functor. Yeah, so that's the story for Frobenius kernels. So that's basically it for actual content. I do want to issue a warning that it's not the case that these statements about co-limits of pointed Tanakian categories always descend to the Grothendieck ring. I don't know for co-equalizers. I don't have an example where it fails for co-equalizers, but it does fail for push-outs. So it is, I can have a push-out of pointed Tanakian categories, which does not descend to a push-out of rings for the Grothendieck rings. So I don't know. And so a problem is just, I want to understand when this holds. I mean, in particular, it clearly holds for Frobenius fixed points and Frobenius kernels. So that there should be some condition for when this holds. And I'm at a loss for now. And then in a sort of sub problem of this that I think is interesting and might be interesting to people here, is a lot of this still works in characteristic 0. So now I don't go all the way up to the algebraic group G, but if I go up just to the FQ squared points, I have a Frobenius twist from GFQ, FQ squared to GFQ squared. And the fixed points are the FQ points. And so by the same kind of formalism, we get that this is a co-equalizer diagram in the category of pointed Tanakian categories. And I have no idea, does this descend to a co-equalizer of rings? And if not, can we describe what else is in the kernel? And I highly think it's interesting because I don't know, I don't know much about either the monoidal structure or restriction for representations of finite groups of Lie type in this way. So yeah, I don't know. It's I just thought it was an interesting question that maybe one of you can help me think about. But yeah, that's it. Thanks for coming.
Could you leave the
Could
you leave the last slide? Thanks.
I guess in the situation where you you look over GFQ squared, there's I mean, if you're just restricting from GFQ squared to GFQ, I mean, someone will probably tell me I'm wrong, but my general feeling is that this is horrid, trying to determine these restrictions. So typically here, what you want to look at is what's known as Shintani descent, which is, but this is something that's really only kind of defined at the level of class functions and doesn't doesn't really have an interpretation at the categorical level. So, but yeah, I've never tried to. Probably TF has tried to restrict things from GFQ squared to GFQ, but I haven't, because I'm not brave enough. Actually, maybe I'll ask a question. Do you get so you kind of touched on this. You were talking about this Brunner-Lubeck. So do you get any kind of sense or interpretation for the image of this restriction map, or like the failure of it to be surjective, or like any kind of interpretation of the co-kernel or something?
Well, so this may hold for arbitrary reductive groups. I tried proving it and got stuck somewhere, but like at no point did I actually find a counterexample. I mean, there's a lot of like, you know, in the description, there's a lot of like, you know, you pass to some subgroup and then you look at them, that has a cover by some simply connected cross torus thing. And like, there's a lot of you're sort of, you know, going down to something finite index with a cyclic quotient and then back up. And so there's a lot of chasing around and I couldn't quite get it to work, but I don't know if it fails. But I think if it goes wrong, it's like, there's just some like cyclic group somewhere that screws you up slightly. So only, yeah, but I don't know. I don't know completely, but I at least the parts of the proof I was having trouble getting to work were really just about some sort of like isogeny issues.
And if your K0 statement were true for reductive groups, would it follow that it's true for all groups?
Yeah. So passing from an arbitrary or let's say connected. So there's definitely an issue if you're not connected of whether or not the Frobenius acts trivially on components. But if you're connected, then well, K0 of representations of a connected group is the same as K0 of representations of its reductive part. Right, kind of the non-reductiveness is just giving you more extensions, which we don't see.
It seems kind of remarkable that you have this family where, like, just of rings, if you write, is that right? Can you make a family with a parameter t such that t equals 1, the co-equalizes the g of fq points, and at t equals 0, it's the representations of the Frobenius kernel?
I don't like, so I mean, you sort of want to be going between the, you know, you're sort of trying to interpolate between the identity map on your group and the send everything to the identity map on your group. And I certainly don't think you can do that sort of at the group level. But yeah, that's a good point. Like realizing these co-equalizers and putting it in some family like that could be nice. Yeah.
And do you think your results could have applications for X computations? Or?
Yeah, I don't know. I mean, so it's kind of, you know, I sort of set out, you know, trying to do this and hoping that I could say something new about representations of the news. I sort of can't. At least so far. I think part of it is, I mean, the idea what I wanted to do and spend a lot of time trying to think about is like, can I then, you know, describe these co-equalizers kind of purely on the categorical side, there, and that seems hard. And you know, I have some ideas. I have some ideas for how one could show that, like, you know, co-equalizers always exist without passing through Tanakian formalism and back. But like, even that description is some sort of messy thing, and so it's not clear how to extract useful information out of it yet. But you know, this is very much in progress. I've sort of been making this all up while I've been here at the IAS. So that's definitely one of the things I would like to understand is, can we use this perspective to get information about X, or about even just like projective objects? It's not clear how that fits into this picture. Yeah, hopefully soon.
And can you drop, so here you're saying the co-equalizer and Tanakian categories, so in particular you want them to be symmetric. Can you drop things like this? Like, just consider this in a bigger category? Like, I understand that this proof wouldn't work, but something.
Yeah, so you don't have this, but like I do think it's reasonable to expect that, say we have like you know, like we can think of like the small quantum group as being somehow analogous to the Frobenius kernel.
Mm-hmm.
And so it's probably true that we can formulate you know, something like representations of the small quantum group as some sort of co-equalizer of some representations. But I'm not sure what the right setup for that is, and yeah, what the right relaxation of Tanakian formalism is.
Okay.
I guess I should say there is you can relax Tanakian if you relax it to braided. I think you're still okay. There's a Hopf algebra version of Tanakian formalism. So maybe what I said about quantum groups is actually tractable. I'm not sure.
Okay. Mm-hmm.
If you happen to have like a natural transformation between the two functors that you're taking the co-equalizer of, what structure does that give you on the co-equalizer?
I mean, I think it should give you a natural transformation of the identity functor, maybe.
You don't want any of those, right?
Yeah. Well, no, you can have, you know, some. I mean, what, like a natural transformation of the identity functor of, if I'm in representations of a group, that's just like an element of the center of the group algebra.
Is that true? I guess so, yes.
Yes, that's correct.
Sorry, I was thinking about anamorphism of the monodal identity, and obviously that's different.
Yeah, but I'm not 100% sure, Ben. I think.
Oh, but wait, if it's also monoidal.
Monoidal, yeah.
That gives you even more, right?
That should give even more. Yeah, that should.
If it's monoidal, it's at the center of the group, not just the group algebra, center of the group.
Right. No, I was just thinking, like, if you, well, okay, now this is obvious. Right? I was thinking that if you start now, you have some group with an element in the center of the group, and you can force the eigenvalue to be a particular thing, maybe in this way. And in that case, there seems like there's a.
Yeah, I don't know. I think yeah, there's in many ways, I think this really raises more questions than it answers. But hopefully this perspective, I think, kind of clarifies, at least to me, what's really going on here.
In this push out example that you say fails, is it like you can construct the push out as a co-product and then co-equalize it?
Yeah, so I'm sort of cheating. So if you have one, say we have one ambient group, and I have inside of it two subgroups, then their intersection forms a pullback in the category of groups. So on the Tanakian side, that forms a push out of point Tanakian categories. But then if we look at the level of Grothendieck rings, we can't tell the difference between a group and a conjugate. So so under that description, I at the level of rings, I can't tell the difference between a group and a subgroup and a conjugate of it. So I can't tell the difference at the level of rings between the intersection of G and H and the intersection of G and some conjugate of H. And those can just be totally different groups and have totally different Grothendieck rings. So that's how you would construct a counterexample. Have I actually done it? No. But that's how you do it. I don't have an actual example though.
But could that be an example for a co-equalizer? Or do you think it would fail in the co-product part?
Wait, sorry, what?
Like the push out, you can construct as a co-product and then a co-equalizer. So it has to fail in one of the two steps.
Yeah, so I think it fails in the co-product.
Okay.
But I'm not sure. And I think the more interesting question to me is when does this hold? What like why does it hold in this case or these cases? One more fun thing I'll say about Frobenius kernels is you know do a mixed version of these two theorems. So if I take my two maps to be, say, the Frobenius twist and the square of the Frobenius twist, then the co-equalizer corresponds to the points that become Frobenius fixed once you Frobenius twist them once. So this is like this is the seminar product of the Frobenius kernel and the FQ points, and you can kind of mix these things around, and that this then tells you sort of exactly what we should expect the representation theory of that algebraic group to be. I thought it was cute.
Okay, well, maybe that's all the questions for Nate.